Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about potential errors when performing hypothesis tests. All right, so before we start that, interpreting the p-value. A p-value is actually a conditional probability. It tells us the probability of getting results at least as unusual as the observed statistic, given the null hypothesis is true. So what's the probability of getting what we got, like our p-hat value, or something greater or smaller or different if the null hypothesis is actually true, all right? So there is a p-value percent chance of getting our sample or something more extreme purely by chance if the null hypothesis is true, is how we're going to interpret it. All right, so let's do some examples. If our null hypothesis is p equals 0.92, and we're talking about this is the seed germination rate, our alternative is that p is less than 0.92. Our sample statistic is p hat is 0.855, and our p-value that we got was 0.0004, so that's a pretty small p-value. So there is a 0.04%. I changed it from a decimal to a percentage by moving it over 2 places. So there's a 0.04% chance of getting a sample where 85.5% or less seeds germinate if it is true that 92% actually germinate. All right, we're going to do another example. Our null hypothesis is p equals 0.3, and this is the percent of twin births. The alternative is that it's not equal to 0.3. Our statistic that we got was 1.706%, and our p-value was 0.1004. All right, so that's a pretty large p-value. All right, so there is a 10.04 percent chance of getting a sample where 1.7 or something more extreme of births are twins if it is true that the percentage of twin births is actually 3%. Okay? All right, so now into the errors. So the error happens when we make a wrong decision, right? So if we reject the null hypothesis, but the null hypothesis is actually true, that would be a type 1 error. If I fail to reject the null hypothesis and the null hypothesis is false, then that would be a type 2 error. Okay? Type 1 error is going to be equal to our alpha. It's going to happen, whatever your alpha value is, it's going to happen that percentage of the time. Type 2 error is beta. And if we reject the null hypothesis and the null hypothesis is false, that would be a good thing, and that is the power. If I fail to reject the null hypothesis and the null hypothesis is true, then I also made the correct decision. All right. So sometimes it helps if you think about this in terms of a jury trial. All right, so somebody can either be found guilty, they're convicted, or acquitted, not found guilty. And then really the truth is either if they're innocent or guilty. All right, so sometimes we don't actually know if they really were innocent or if they really were guilty. Sometimes we just don't have enough evidence, right? So if they are convicted, but really they were innocent, then that would be a type 1 error. If they were acquitted, but really they were guilty, that would be a type 2 error. Alrighty. And it's no error if they were convicted and they were guilty, that is not an error. That is the power. And if they were acquitted but they were innocent, that is also not an error. All right, so in a type 1 error, we reject the null hypothesis when the null hypothesis is true. We conclude that the alternative hypothesis is true when really the null hypothesis was true. All right, the probability of a type 1 error is going to be equal to whatever our alpha value is. A type 2 error is when we're failing to reject the null hypothesis and the null hypothesis is false. All right, so we conclude that the null hypothesis is still true when really the alternative hypothesis was true. The probability of a type 2 error would be equal to beta. All right, power is the probability of rejecting the null hypothesis when the null hypothesis is false, so concluding that the alternative is true and being correct. All right, so power is a good thing. The probability of power is equal to 1 minus beta, so 1 minus the probability of a type 2 error. Calculating the probability, or calculating the power, we don't really do that in this course, but power is considered adequate when it's above 80%. All right, increasing the power. There are two things that we can do to increase the power. We can increase the sample size, or we can increase our alpha value. All right, so this gives us a larger chance to reject the null hypothesis, but it also increases the risk of a type 1 error, so keep that in mind. All right, in Philadelphia, it is believed that 12% of motorists run red lights. The city planners decide to put a few traffic cameras that will issue tickets to drivers that run red lights. After 2 months, they check out a few corners where the cameras had been installed. They found that out of 240 drivers that had the opportunity to run the red light, 15 did so and were issued tickets. Does this provide evidence of a decline in the percentage of drivers that run red lights? Using a level of significance of 5%, assume the conditions are met already. All right. So our alpha value is 5%. We're going to kind of do our state plan do conclude thing here. So does this provide evidence? Would be a hypothesis test. P, my proportion is the true proportion of drivers that run red lights. My null hypothesis would be that it's equal to 12%, which was the claim. The alternative is that it's less than 12%. They're asking if there's evidence of a decline. P hat was 15 out of 240, which was 0.0625 or 6.25%, and alpha was 5%. We are doing a 1 proportion Z test. They told me the conditions were already met, so I'm not going to check those. I'm also not going to put everything here since this is not what we're going over right now, but I should have more details here. All right, so my statistic minus my parameter divided by my standard deviation of my statistic gives me a z-score of negative 2.7412 and a p-value of 0.003. Ideally, we would draw our normal curve, shade it, label it, have the formula without numbers plugged in, all of the things. All right, our conclusion here would be we reject the null hypothesis because our p-value of 0.003 is less than our alpha value of 0.05. We have sufficient evidence that the percentage of drivers that run red lights decreased. All right. In other words, the cameras, adding the traffic light cameras in, it worked. All right, so now we're going to look at what would a type 1 error or type 2 error or power look like in this context. So what is a type 1 error in this context, and what is its probability? So a type 1 error, again, is when we reject the null hypothesis, but we are wrong. All right, so concluding that the percentage of red lights run is less than 12%, when really it has not decreased. So concluding that the cameras worked when really they did not would be a type 1 error. Failing to reject the null hypothesis and being wrong would be a type 2 error. This would be concluding that the percentage of red lights run has not decreased when really it has decreased. Concluding that the cameras didn't work when really they did. Back to part 2, I forgot to mention the probability of a type 1 error would be equal to our alpha value, which is equal to 5%. So there's a 5% chance of a type 1 error. And then describe what power means in this context. So power is when you reject the null hypothesis and you are correct. So the probability of concluding that the cameras worked, and they really do. All right. If they had used a level of significance of 1%, what would have happened to the type 1 error, type 2 error, and the power? Okay, so if instead of 5% significance, I went to 1% significance, so I decreased my alpha value. So if I decrease my alpha value, I would be decreasing my type 1 error because the type 1 error is equal to alpha, the probability of it happening. If I decrease alpha, then I'm going to be decreasing the power, right? My power is going to decrease as alpha decreases. And if I decrease my power, that means my type 2 error is going to increase because those are opposites. Remember, power is 1 minus beta, and beta is the probability of a type 2 error. So those are always going to be opposite of each other. All right. How could they have increased the power without changing the level of significance? All right, so if I want the power to stay, or if I want the level of significance to stay the same, which means the type 1 error would stay the same, I could increase the sample size. So if I increase the sample size from 250 to 500, increasing the sample size would increase my power. If I increase my power, then I decrease the probability of a type 2 error. Okay. right, significance level. When we reject the null hypothesis, when our p-value is less than our alpha value. If our alpha value is 0.05, which of the following p-values would be significant? So anything less than 0.05, 0.02, 0.034, the rest of those would not be significant. A researcher developing scanners to search for hidden weapons at the airport has concluded that a new device is significantly better than the current scanner. He made this decision based on a test using an alpha value of 0.05. Would he have made the same decision at an alpha value of 0.1? How about an alpha value of 0.01? Explain. All right, so our conclusion was that it was significant at an alpha value of 0.05, which means our p-value is some value less than 0.05. Well, if my alpha value was 0.1, I know that my p-value is going to be less than that because it was less than 0.05. So yes, I would make the same conclusion at 10% level of significance. At a 1% level of significance, maybe I would need to know what the p-value is. All right, I would need more information. All right, confidence intervals and tests. So confidence intervals are two-sided. They match the confidence level and the alpha value when the alternative is a not equal to test. When doing a one-sided test, if the alternative is a less than or greater than, we double the alpha value to make it two-sided, then match it to the confidence level. So what confidence level is appropriate for an alpha value of 0.03 if I'm doing a one-sided test? My alternative is a less than, so it's a one-sided test. So here's my normal curve. I know that one side, my alpha value is 3% for a one-sided test. So that means I have 3% on the other side, which means I have 94% in the middle. So this would be a confidence level of 94%. What confidence level is appropriate for an alpha value of 0.06 if this would be a not equal to or a two-sided test? All right, so here's my normal curve. I know that both of the tails have to make 6%. So that means it's 3% on either side, which still makes it a 94% confidence level. All right, if I create a 95% confidence interval and want to use it to test the following hypotheses, what would be the correct alpha to use for my conclusion? All right, so if I have a 95% confidence interval, that means I have 95% in the center. If I have 95% in the center, I have 2.5 on either tail. And so if I'm doing a one-sided test, my alpha value would be 0.025 or 2.5%. And if I'm doing a two-sided test, I would combine those and it would be a 5% or 0.05. All right. In August 2004, Time magazine reported the results of a random telephone poll commissioned by Spike Network. Of the 1,302 men who responded, only 39 said that their most important measure of success was their work. Estimate the percentage of all American males who measure success primarily from their work. Use a 98% confidence level. Check the conditions first. Okay, so again, we're going to kind of do some of this, and it's not going to be super thorough. Random was stated they did a random poll, 10%. 1,302 is less than 1/10 of all working men. Large counts, I'm going to do n times p. I don't have p, so I'm going to use p hat, which is 0.03, which I got by doing 39 divided by 1,302. So I checked that. Those are greater than 10. So my conditions are met, and this I'm doing a 1 proportion Z interval. Okay, it asks me to estimate the percentage. So when you see that type of question, it's an interval. When it says, do the data provide convincing evidence, it's a hypothesis test. All right, so my interval is p hat plus or minus z star for 98% would be 2.362 times the standard deviation, or the standard error here. All right, and I get an interval 0.0189 to 0.0409. So we are 98% confident that the interval from 0.0189 to 0.0409 captures the true proportion of men who said work was a good measure of success. All right. Some believe that few contemporary men judge their success primarily by their work. Suppose we wish to conduct a hypothesis test to see if this fraction has fallen below 5% mark. What does your confidence interval indicate? So we're not actually going to do the test, but what our confidence interval indicate? So if we were to do the test, my null hypothesis would be that p equals 0.05, and the alternative would be that it's less than 0.05. Well, since 0.05 is not in our interval, we do not believe that that value, 0.05, is true. The entire interval is below 0.05, so we can conclude that the percent has decreased below 5%. What is the level of significance for this test? So if I was going to do the test, what significance level? So my confidence level was 98%, and then it was a one-sided test. We were doing a less than test. So I want to figure out what that alpha value would be. So I have my normal curve, 98% in the middle. That leaves me with 2%, 1% on either side. Because it's a less than test, I'm only concerned with that one tail, so my alpha value would be 0.01. All right, go Seahawks.